this is the 9A problem set. So let's take a look. There we go. So for number 4, the molecule shown here is difluoromethane, CH2F2. You can see it over on the right-hand side. Based on the structure, how many electron domains surround the structure, the central atom. So that would be 1, 2, 3, 4. 4 electron domains. Because it's carbon, carbon has 4 places to bond so that there are no lone pairs there. They're all actual bonds. So based on the number of electron domains, the structure is tetrahedral. There are 4, so it's tetrahedral. Would the molecule have a non-zero dipole? And the answer to that is yes, it would be non-zero. And the reason why it would be non-zero, in other words, in certain situations, if we had CH4 or CF4, you would have no dipole. You would have no polarity. It would be nonpolar because all 4 bonds would result in an atom that has the same electronegativity around all 4. So geometry would make a difference. However, in this case here, with the F, if we have the green for F here and the white for H here, that means that I start off with something that looks like an arrow pointing towards the negative part of this. We make a little plus sign at the bottom end where the H's are, and the arrow points up towards the more negative area, which would be up where the F's are with the green atoms. Okay, so that would be how we would mark. That would be how we would mark what direction the negativity would be moving, or what direction it would flow. So the molecule has a non-zero dipole, and the answer would be yes. The molecule has a non-zero dipole. If the molecule is polar, what direction would the overall dipole moment vector point in the molecule? It would point towards the fluorine, okay, through the hydrogen, through the central atom, up to the fluorine. Moving on, 12, methane, CH4, and perchlorate, ClO4 minus 1, are both described as tetrahedral. What does this indicate about their bond angles? Okay, so what it indicates is that we see a CH4. I'm going to have a tough time drawing this. It's going to look CH4. I'm really not good. There's one that comes out in front and one that goes in the back, like that. Something, that's not what it looks like. But anyway, each of these bond angles, though, are 109.5 as long as there are no lone pairs. And the Cl, so we got, I think we might have like 2 or 3 double bonds, maybe 2. And like that. So we're going to have basically 109.5 bond angles for both of these, even though notice that we count, and I'm going to use a different color for this, whether it's a single bond or a double bond, that counts as 1 electron domain. That's important. I don't think chlorine has any other kind of, I think they'd have to be a double bond. Well, no, it could be a coordinate covalent bond. But either way, 1 electron domain, it equals single, double, or triple bond. Okay, so that's all just 1 electron domain, and that's how we calculate it. The NH3 molecule is trigonal pyramidal. How many parameters needed to be specific to define the geometry? So in NH3, notice that we start off with the structure like this, and then always we count the number 1, 2, 3, 4. 4 is tetrahedral. There we go. Tetrahedral for electron domain. Okay, but because it's 3 bonds and 1 non-bonding, that's where our trigonal pyramidal comes from. That's trigonal bipyramidal. Okay, because it's 3 and 1. Check the in class. We're going to definitely go over if you have my in-class class. We will definitely go over the chart, and I will have to post something separate from my online class so they can see how I fill that chart out. All of the information is definitely in the book on in section 9.2, I believe it is, where we go through all of the separate, the 5 different geometries, electron domain geometries. Okay, so I think I answered everything there. How many parameters? You need to know 2 things. You need to know how many electron domains and how many are non-bonding. If you know how many electron domains there are and how many are non-bonding, you can find out what the molecular geometry is from that information. So 2 domains, or two things to know. How does one determine the number of electron domains in a molecule or an ion? Okay, you are counting bonds and lone pairs of electrons, such as oxygen, like that. You count bonds, 1, 2, and lone pairs, 3, 4. Okay, this is tetrahedral for electron domain. Oops. Okay, for electron domain, it's tetrahedral, and then because there are 2 non-bonding means what we have for the molecular geometry is bent, B-E-N-T, for water, which is why it looks the way it does. Okay, that would be tetrahedral for electron domain, but molecular geometry is bent. Okay, what is the difference between a bonding electron domain and a non-bonding electron domain? Well, one of the differences is that if we have all bonding domains like this, we get a 109.5. But if we have a non-bonding domain like this, it takes up more room, and that makes this a little bit less, 107. If we have 2 non-bonding domains like this, it makes this even smaller, 104, because that one takes up more room and this one takes up more room, like that. So the difference between bonding and non-bonding is the non-bonding actually takes up more room than the bonding does. The reason is because when you have bonding, like in this situation here, where you have H, and you have a bonding thing that, like a bonding area that is now being stretched between 2 atoms, when non-bonding tends to be flatter and take up more room around the immediate central atom. And that really it changes the angle a little bit more for the other bonding angles. So let's keep going. 18AB3 molecule is described as having trigonal bipyramidal electron domain geometry. Okay, so how many non-bonding domains are on the atom? Well, I put this, here we got trigonal bipyramidal, which is the electron domain geometry. If we have all 5 that are bonding, that would be trigonal bipyramidal as the molecular geometry. Okay, now this says it's AB3, so this one right here would be AB5. What if you take away one of the bonds and replace it with a non-bonding? That would be AB4. As I go down here, you can see the next one here would be AB3, okay? And that actually ends up being T-shaped. Notice you have the non-bonding here, non-bonding there, and that's where the part comes in where it's T-shaped, because it looks like that. Remember, for trigonal bipyramidal, if you listen to the section screencasts, that when we have trigonal bipyramidal, I start to take bonds away from the equatorial bonds. I start to replace those with non-bonding pairs, and that's that. There are axial bonds, and then there are equatorial bonds, and we take the equatorial bonds first. Okay, so let me just make sure I answered this question correctly. and finished it. How many non-bonding domains are on the atom? Well, if all of them were bonds, it would be AB5. So because it's AB3, that means you have 2 non-bonding pairs. 2 non-bonding pairs. Okay, because if it's trigonal bipyramidal and all of them are bonds, you would have AB5. But because this tells us it's AB3, I simply subtract the 2, and that tells me I have 2 non-bonding pairs. Moving on. Give the electron domain and molecular geometry for the following molecules and ions. Okay, let's go through. Let me see which ones here. I want to do a couple and then have you guys finish them. So I got 3 here. Let's take a look at letter B, because I think that's going to be a more difficult one. We're looking for the electron domain and we're looking for the molecular geometry. So before you do anything, you got to figure out what the central atom is. The central atom is this. So if S is the central atom between SO3 with a -2, I'm writing always, my first step is to write the Lewis structure. So we have to practice writing Lewis structures, and we got to pick a structure that's going to be like the most stable. So we'll take a quick look at this and see if we can find the most stable structure. Here's my Lewis dot diagram. Here's my dot diagram for sulfur, where I have 2 pairs and 2 single electrons. And then I have 3 oxygens. Now, I know that this means it's a polyatomic ion, and I know that that also means that 2 of the oxygens are going to be in single single bonds, like that. And then I do this, because I've done this a couple of times now. The other one's going to be a double bond, like that. There, like that. And now my -2. Remember, when we add these up, we get 6 plus, that's 18 equals, 24, and then plus another 2 electrons equals 26. So right now I have 1, 2, 3, 4. I'm going to start on the oxygen on the left-hand side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I got 24, so I need 2 more. And because we have the extra 2 here and here, I put an extra one there and an extra one here. I screwed that up before, like that. So now I have 26 electrons throughout here. My next step is to, of course, put the, like that. Now, here's the whole reason why I did this. I wrote out the Lewis structure so I could take a look at the central atom. Central atom has 1, 2, 3, 4. Okay, so electron domain equals tetrahedral. Okay, electron domain equals tetrahedral when there are 4. Now, how many are bonds and how many are non-bonding? Okay, so it looks like this. I have 1, 2, 3. I have 1, 2, 3 that are bonding and 1 that's non-bonding. So if it's 3 bonds and 1 non-bonding, that is, on the chart, it says trigonal pyramidal. And that is our, molecular geometry. Molecular geometry. Okay? So electron domain is tetrahedral, and because it's 3 bonds, excuse me, because it's 3 bonds, the double bond counts as 1 electron domain. It's 3 bonds and 1 non-bonding. That gives us trigonal pyramidal. All right, let's move on. Oh, there's 6 here. Well, let's do another one then. Screw it, let's do another. And then I'll stop for this one. And how about letter D? So I got P as my central atom. Looks like this, but P can also look like this. like that. Now here's what I know. I know all of the F's are going to be coming off of the P. So what I'm going to do is I'm going to put the extra, this -1 that we have here, I'm going to do the -1 like this, and I'm going to add it on to oxygen like that. Or not oxygen, to phosphorus like that. And then I'm just going to simply connect all fluorine like this off of each one of these, like that. Here's why I have to do that. Fluorine can't have more than one bond. The reason why it can't is because it can only have an octet because it's in the second period. It's not like chlorine or bromine that can have an expanded octet. So when I do this like this, the only thing that can have an expanded octet would be phosphorus. Fluorine can't do it because it's in the second period. So that's why I take my extra electron there, -1, and I place it on phosphorus so that I can fit all 6 bonds with fluorine going around the outside. What would be, now, what about the electron domain geometry? How many bonds and non-bonding do I have? I have 1, 2, 3, 4, 5, 6. 6 is octahedral for electron domain. Okay, and because there are no non-bonding, it is 6 and 0. That would be, again, octahedral for molecular geometry. Okay, that's it for part 1.